Welcome back. In this session, we introduce the idea of cylinders. Not only the idea, but discuss in detail different cylinders through examples and figures. After that, we move on to the quadric surfaces. We examine certain quadric surfaces like ellipsoid, hyperboloid, paraboloid, etc. Definition: a cylinder is a surface generated by a line which is always parallel to a fixed line and passes through a given curve. That is, a cylinder is a surface composed of all lines that lie parallel to a given line in space and pass through a given plane curve. The fixed line is called the axis of the cylinder and the given plane curve is called a guiding curve or generating curve. Note 1. If the guiding curve is a circle, the cylinder is called a right circular cylinder. Since the generator is a straight line, it extends on either side infinitely. As such, a cylinder is an infinite surface. The degree of the equation of a cylinder depends on the degree of the equation of the guiding curve. A cylinder whose equation is of second degree is called a quadric cylinder. Definition: enveloping cylinder. The locus of the lines drawn in a given direction or parallel to a given surface is called the enveloping cylinder of the surface. Equation of the enveloping cylinder of a sphere. To find the equation of the enveloping cylinder of the sphere, x square plus y square plus z square plus 2ux plus 2vy plus 2wz plus d is equal to 0, whose generators are parallel to the line x by L is equal to y by m is equal to z by n. Let alpha, beta, gamma be any point on the surface of the cylinder so that the equations of the generator through these points are x minus alpha by L is equal to y minus beta by m is equal to z minus gamma by n, which is equal to r. Any point on this line is alpha plus Lr, beta plus Mr, gamma plus Nr. If it lies on the given sphere, we have alpha plus Lr whole square plus beta plus Mr whole square plus gamma plus Nr whole square plus 2u into alpha plus Lr plus 2v into beta plus Mr plus 2w into gamma plus Nr plus d is equal to 0. The roots of the equation is L alpha plus m beta plus n gamma plus Lu plus mv plus nw whole square is equal to L square plus m square plus n square into alpha square plus beta square plus gamma square plus 2u alpha plus 2v beta plus 2w gamma plus d. This is the required equation of the enveloping cylinder of the given sphere. Note 2. In solid geometry, where cylinder means circular cylinder, the generating curves are circles, but here generating curves are of any kind. See figure 1. When graphing a cylinder or other surface by hand or analyzing one generated by a computer, it helps to look at the curves formed by intersecting the surface with planes parallel to the coordinate planes. These curves are called cross sections or traces. Example 1. The parabolic cylinder y is equal to x square. Find an equation for the cylinder made by the lines parallel to the z axis that pass through the parabola y is equal to x square, z is equal to 0. See figure 2. Solution. Suppose that the point P0, x0 square 0 lies on the parabola y is equal to x square in the xy plane. Then for any value of z, the point Q x0 square z will lie on the cylinder because it lies on the line x is equal to x0, y is equal to x naught square through p naught parallel to the z axis. Conversely, any point q x naught square set whose y coordinate is the square of its x coordinate lie on the cylinder because it lie on the line x is equal to x naught, y is equal to x naught square through p naught parallel to the z axis. See figure 3. It is known as the cylinder y is equal to x square. Example 2. The equation x square plus y square is equal to 1 define the circular cylinder made by the lines parallel to the z axis that pass through the circle x square plus y square is equal to 1 in the xy plane. Example 3. The equation x square plus 4y square is equal to 9, that is the equation x square by 3 square plus y square by 3 by 2 whole square is equal to 1, defines the elliptical cylinder made by the lines parallel to the z axis that passes through the ellipse x square plus 4y square is equal to 9 in the xy plane. In a similar way, we have the following. As example 1 suggests, any curve f of xy is equal to c in the xy plane define a cylinder parallel to the z axis whose equation is also f of xy is equal to c. Any curve g of xz is equal to c in the xz plane defines a cylinder parallel to the y axis whose space equation is also g of xz is equal to c. Any curve h of yz is equal to c defines a cylinder parallel to the x axis whose space equation is also h of yz is equal to c. Summarizing the above, we have an equation in any two of the three Cartesian coordinates defines a cylinder parallel to the axis of third coordinate. Example 4. The equation y square minus z square is equal to 1 defines surface made by the lines parallel to the x axis that passes through the hyperbola y square minus z square is equal to 1 in the yz plane. Quadric surfaces. A quadric surface is the graph in space of a second degree equation in x, y and z. The most general form is ax square plus by square plus cz square plus dxy plus eyz plus fxz plus gx plus hy plus jz plus k is equal to 0, where a, b, c, d, e, f, g, h, j, k are constants. But equation can be simplified by translation and rotation as in the two-dimensional case. We will study only the simpler equations. Although the definition did not require it, the cylinder considered here are also examples of quadric surfaces. We now examine ellipsoid, paraboloid, cone and hyperboloids. Example 5. The ellipsoid. See figure 5. X square by a square plus y square by b square plus z square by c square is equal to 1. Equation number 1 cuts the coordinate axis at plus or minus a 0 0, 0 plus or minus b 0 and 0 0 plus or minus c. It lies within the rectangular box defined by the inequalities mod x less than or equal to a, mod y less than or equal to b and mod z less than or equal to c. The surface is symmetric with respect to each of the coordinate planes because the variables in the defining equation are squared. The curves in which the three coordinate planes cut the surface are ellipses. They are x square by a square plus y square by b square is equal to 1 when z is equal to 0. X square by a square plus z square by c square is equal to 1 when y is equal to 0. A y square by b square plus z square by c square is equal to 1 when x is equal to 0. The section cut from the surface by the plane z is equal to z0 mod z0 less than c is the ellipse x square by a square into 1 minus z0 by c square plus y square by b square into 1 minus z0 by c square is equal to 1. Equation number 2. Example 6. The elliptic paraboloid. See figure 6. X square by a square plus y square by b square is equal to z by c. Equation number 3. Is symmetric with respect to the planes x is equal to 0 and y is equal to 0 as the variables x and y in the defining equation are squared. The only intercept on the axis is the origin 0, 0, 0. Except for this point, the surface lies above or entirely below the xy plane, depending on the sign of c. The sections cut by the coordinate planes are x is equal to 0, the parabola z is equal to c by b square into y square. Y is equal to 0, the parabola z is equal to c by a square into x square. Z is equal to 0, the point 0, 0, 0. Equation number 4. Each plane z is equal to z0 above the xy plane cuts the surface in the ellipse x square by a square plus y square by b square is equal to z0 by c. Example 7. The circular paraboloid or paraboloid of revolution. X square by a square plus y square by a square is equal to z by c. Equation number 5 is obtained by taking by b is equal to a in equation 3 for the elliptical paraboloid. The cross sections of the surface by planes perpendicular to the z axis are circles centered on the z axis. The cross sections by planes containing the z axis are congruent parabolas with a common focus at the point 0, 0, a square by 4c. Applications. Shapes cut from the circular paraboloids are used for antennas in radio, telescopes, satellite trackers and microwave radio links. We have already discussed that a cone is a surface generated by lines, all of which pass through a fixed point called vertex, and all the lines intersect a given curve called guiding curve, or all the lines touch a given surface, or all the lines are equally inclined to a fixed line through the fixed point. The moving lines which generate a cone are known as its generators. When the moving lines satisfy condition 2 in the definition of a cone, we term the cone as enveloping cone. In figure A, all the generators pass through the vertex V and cut the curve C, while figure B, all the generators pass through the vertex V and touch the given sphere S. Example 8. The elliptic cone. X square by a square plus y square by b square is equal to z square by c square. Equation number 6. Is symmetric with respect to the 3 coordinate planes. See figure 7. The sections cut by the coordinate planes are x is equal to 0, the lines z is equal to plus or minus c by b y. Equation number 7. Y is equal to 0, the line z is equal to plus or minus c by a x. Equation number 8. Z is equal to 0, the point 0, 0, 0. The sections cut by planes z is equal to z0 above and below the xy plane are ellipses whose centers lie on the z axis and whose vertices lie on the lines in equations 7 and 8. If A is equal to B, the cone is a right circular cone. Example 9. The hyperboloid of one sheet x square by a square plus y square by b square minus z square by c square is equal to 1. Equation number 9 is symmetric with respect to each of the 3 coordinate planes. See figure 8. The sections cut out by the coordinate planes are x is equal to 0, the hyperbola y square by b square minus z square by c square is equal to 1. Y is equal to 0, the hyperbola x square by a square minus z square by c square is equal to 1. Question number 10. Z is equal to 0, the ellipse x square by a square plus y square by b square is equal to 1. The plane z is equal to z0 cuts the surface in an ellipse with the center on the z axis and vertices on one of the hyperbolas in 10. If A is equal to B, the hyperboloid is a surface of revolution. Remark: the surface in example 9 is connected, meaning that it is possible to travel from one point on it to any other without leaving the surface. For this reason, it is said to have one sheet, in contrast to the hyperboloid in the next example, which has two sheets. Example 10. The hyperboloid of two sheets, z square by c square minus x square by a square minus y square by b square is equal to 1. Equation number 11 is symmetric with respect to the three coordinate planes. See figure 9. The plane z is equal to 0 does not intersect the surface. In fact, for a horizontal plane to intersect the surface, we must have mode z greater than or equal to c. The hyperbolic sections x is equal to 0, z square by c square minus y square by b square is equal to 1, y is equal to 0, z square by c square minus x square by a square is equal to 1 have their vertices and foci on the z axis. The surface is separated into two portions, one above the plane z is equal to c and the other below the plane z is equal to minus c. This accounts for the name hyperboloid of two sheets. Equations 9 and 11 have different numbers of negative terms. The number in each case is the same as the number of sheets of the hyperboloid. If we replace the one on the right side of either equation 9 or equation 11 by 0, we obtain the equation x square by a square plus y square by b square is equal to z square by c square. For an elliptic cone, equation 6. The hyperboloids are asymptotic to this cone in the same way that the hyperbolas x square by a square minus y square by b square is equal to plus or minus 1 are asymptotic to the lines x square by a square minus y square by b square is equal to 0 in the xy plane. Example 11. The hyperbolic paraboloid y square by b square minus x square by a square is equal to z by c, c greater than 0. Equation number 12 has symmetry with respect to the planes x is equal to 0 and y is equal to 0. Figure 10 below. The sections in these planes are x is equal to 0, the parabola, z is equal to c by b square y square. Equation number 13. Y is equal to 0, the parabola, z is equal to minus c by a square into x square. Equation number 14. In the plane x is equal to 0, the parabola opens upward from the origin. The parabola in the plane y is equal to 0 opens downward. If we cut the surfaces by a plane z is equal to z0 greater than 0, the section is a hyperbola. Y square by b square minus x square by a square is equal to z0 by c. Equation number 15 with its focal axis parallel to the y axis and its vertices on the parabola in 13. If z0 is negative, the focal axis is parallel to the x axis and the vertices lie on the parabola in 14. Near the origin, the surface is shaped like a saddle. To a person travelling along the surface in the yz plane, the origin looks like a minimum. To a person travelling in the xz plane, the origin looks like a maximum. Such a point is called a minimax or saddle point of a surface. Now, let us summarize the session. Here, we introduce the idea of cylinders followed by so many examples like parabolic cylinders, etc. Next, we defined the quadric surfaces and also discussed some of the surfaces together with the diagram like ellipsoid, hyperboloid, etc. But in the coming sessions, we discuss the nature and shape of quadric surfaces in detail. So, before moving to the next session, let us try to answer the questions. 1. Sketch these surfaces. Cylinders. X square plus y square is equal to 4. Z is equal to y square minus 1. Ellipsoids. 4x square plus 9y square plus 4z square is equal to 36. Paraboloid. Z is equal to x square plus 4y square. Z is equal to 8 minus x square minus y square. Hope you enjoy the session. See you next time. Till then, take care.